We are now on our last module, and this video is about limitations of algorithm power. All throughout the course, we were introduced with a lot of problems and their corresponding algorithms. And in the last few sessions, we were able to classify algorithms according to different design strategies like brute force or exhaustive search, transform and conquer, greedy and dynamic programming. And our measure of a good algorithm is usually through the time complexity or how fast an algorithm runs. So the question now is that given a particular problem, how fast can we really get? Or how can we know if we will stop looking for a faster algorithm? So to answer that, we can compute or prove certain arguments called lower bound arguments on the running time of any algorithms for a particular problem. This module will introduce the concept of lower bound arguments. We will present several methods how we can establish lower bounds, and moreover, we will introduce the concept of P and NP. Certain problems can and cannot be solved in polynomial time. So this is also a preliminary concept for the area called computational complexity. Some of the few important classes of problems are called NP-complete problems and NP-hard problems. We'll also introduce several misconceptions about NP-hard problems. We'll start with the definition of lower bounds. So, the lower bound is an estimate on the minimum amount of work needed to solve a given problem. So, for example, since we are dealing with time complexity, and time complexity is basically the total number of operations, we can think of a lower bound as the total number of comparisons needed to find the largest element in a set of n numbers. Number of comparisons needed to sort an array of size n, number of comparisons necessary for searching in a sorted array, or number of multiplications needed to multiply two n by n matrices. So again, we are counting the total number of basic operations, and for the first three problems here, comparison yung basic operation, and then for the last one, we have multiplication as the basic operation. Note that this is not equivalent to the best case analysis for a particular algorithm. In best case analysis, we are actually measuring the minimum amount of operations that an algorithm does to compute for a particular problem, while here, we are measuring the best possible worst case analysis of any algorithm for a particular problem. So to explain that further, suppose we have a problem P with a corresponding algorithm called alg1. We can assess the time complexity of alg1 using the best, average, and the worst case analysis. And among these types of analysis, the worst case analysis is the most important one because we wanted to know how long our algorithms will run on the worst input. So aside from alg1, of course, we can have more algorithms solving the same problem. So suppose we have alg2 and then alg3. Listing all the worst case analysis time complexity of each algorithm, suppose we have O of n cubed, O of n squared, O of n. In this set, we can say that algorithm 3 is the best algorithm for problem P because it's the fastest among the three algorithms. However, we may ask whether we can still improve this. So this can be answered by statements of the form O of f of n is the minimum amount of work needed to solve P. This is called the lower bound argument for problem P. The lower bound can be an exact count or an efficiency class. If it's an exact count, it could be a constant number or a specific function. The function should be with respect to the size of the input, say n or n squared, where n is the total size of the input. If it's an efficiency class denoted by the omega notation, then it's a group of function that is bounded below by some function inside the omega notation, like this one. So here are some well-known lower bound results. Note that the lower bound results are property of a problem and not a property of a particular algorithm. So for comparison based sorting, the lower bound is n log n. So to rephrase this, for um, for comparison based sorting, we need at least n log n comparisons to sort an input of size n. For search problem in a sorted array, we have omega of log n. To identify whether all elements in an input of size n are unique, we need at least n log n comparisons. And then for n-digit integer multiplication, we need omega of n calls to its basic operation, kung ano man yung basic operation for integer multiplication. And then lastly, for multiplication of two n by n matrices, we have omega of n squared. Okay, so a particular lower bound argument is called tight if and only if there exists an actual algorithm with the same running time complexity. And when we say time complexity, we're referring to the worst case analysis. Know that you can have a lower bound argument even without creating an actual algorithm. And if in case we can create a corresponding algorithm with the same running time complexity, that is even more impressive because we can say that we can have a tight lower bound for a particular problem. So let's examine each of the lower bound arguments and check if this is tight or unknown. So again, if it's tight, there is a corresponding algorithm with the same running time. If the answer is unknown, then the algorithm is still there waiting to be discovered. Okay, so for the first three problems, the corresponding lower bound argument is tight. So let's check each. For sorting, we have merge sort, quick sort with running time complexity of n log n. Okay, so with the lower bound argument for sorting and with existing algorithms with the same running time, we can say that this lower bound argument is tight for sorting. Next is we have search. It is tight for searching in a sorted array because we can simply use binary search to look for items in a sorted array in O of log n time. Okay, so may nag-exist na algorithm for that. And then for element uniqueness, may algorithm ba with n log n running time? Well, I can easily think of sorting, pre-sorting the set of elements and then doing a linear search or probably using yung item number 2. So, n log n for sorting plus log n is still O of n log n. So, yes, it is an algorithm with a running time complexity of n log n for element uniqueness. And then for the last two problems, we have unknown. So, ano ibig sabihin ng unknown? For unknown, ibig sabihin, wala pang nag-e-exist na algorithm na ito yung running time complexity. So, hindi ko pa alam kung ano yung best so far for these algorithms, but I know that for multiplication of n by n matrices, ang naive na method dun is O of n cubed. Okay? Pero there is Strassen's algorithm with a slightly better running time, pero hindi siya umabot ng n squared. From what I remember, it's O of n raised to 2 point something, 2.8 ata or something. So this is still an open problem if you can provide an algorithm with a lower um, running time complexity, or even better if you can provide a tight bound for the multiplication problem. Different methods for establishing lower bounds. The first method is the easiest. The trivial lower bound is obtained by counting the number of items that must be processed in input and generated as output. So, this method relies on the idea that any algorithm for the problem must read or process all the input and write the expected output. The trivial lower bound sometimes provide a useful bound, and often too low to be useful, especially for combinatorial optimization problems. Here we have four problems with their corresponding trivial lower bounds, so ito yung TLB. I also highlighted the size of the input and the output to establish how the trivial lower bound is obtained. So for the first problem, where we generate all our permutations, the input here is a set of n items. So we need to process n for the input. And since the problem is generating all permutations, we need to generate all permutations, and the total number of permutations given n items is n factorial. So just by counting the input and output, we have a trivial lower bound of n factorial. And then for item number 2, evaluating a polynomial of degree n, the input here is x and each of the coefficients of the polynomial. And the output is the evaluation of p of x. So we have n plus 1 and 1 with a bound of trivial lower bound of n. So for item 1 and item 2, these trivial lower bounds are useful because these are actually tight lower bounds for these problems. So meaning we have existing algorithms with this running time and this running time. The third problem is for matrix multiplication. The input here is of size 2n squared. So we have 2n by n matrices, and the output is an n by n matrix. So we have n squared items there. So using this, we have n squared, trivial lower bound. So this is also the lower bound result for matrix multiplication as shown in the previous slide. And this is not yet known to be a tight bound for matrix multiplication. So one example of too lower bound for a problem is for the TSP. So if we evaluate the size of the input and output for the TSP, we can get n squared as the trivial lower bound. But we all know that there is no known polynomial time algorithm for this. So n squared is a very low bound for the traveling salesman problem. The next approach is by using decision trees. Decision trees are often used to model algorithms using comparison as its basic operation. So these are algorithms for searching, sorting, getting the maximum or minimum number in a given array. So here we are showing a decision tree for sorting three unique elements A, B, and C. You can imagine a decision tree is like a rooted tree with internal nodes representing the comparisons or the operations, and the leaf node as a possible output or outcome. So note that in the internal node, each comparison is answerable by a yes or a no or a decision. So Answering that decision will make us choose a particular branch of the tree. A traversal from the root to a particular leaf is a possible computation of an algorithm, and the corresponding leaf for that traversal is the output of the algorithm. Note that in a decision tree, the total number of leaves is at least the total number of unique outcomes. So, bakit pwedeng mas marami yung leaves? Because there are some sequence of computation that can arrive at the same outcome or output. So in this slide, we use the decision tree to provide a non-trivial lower bound for the sorting problem. The items listed here in this slide is the proof idea how to prove such claim. So first is any comparison-based sorting algorithm can be represented by a decision tree. That is for a fixed input size n. So we can create a decision tree. And then the total number of leaves for that decision tree is at least the total number of possible output. So since in sorting, we are looking at the set of all possible permutations of the input elements, we have n factorial. And since I mentioned a while ago that possible outcomes can be greater than the all possible output because there are some comparisons that may arrive at the same outcome, mas marami yung leaves ng decision tree. Okay, so if we have n factorial leaves, the height of the binary tree is log of n factorial, or to be exact, the ceiling of log of n factorial. Okay, so as you may recall, the decision tree a while ago have ano bang tawag dito, hindi pantay-pantay na height. So this isn't necessarily a complete binary tree. Okay, so the minimum number of comparisons in the worst case is log of n factorial. The height of the tree is an indicator of the total number of comparisons. So the longest path from the root to a leaf represents the worst case number of comparisons. So since log of n factorial, yung dami ng comparison or height of the tree na may longest path, this is the lower bound. Okay, so this is just to simplify log of n factorial. By using Stirling approximation, this expression is approximately equal to n log n. Ito ba yung shorthand explanation why this expression is equal to this? So, suppose we have log of n factorial. We know that n factorial is approximately equal to n raised to n. If we get the logarithm of n raised to n, we have n log n. And since we have corresponding algorithms with n log n as the running time, this is a tight lower bound for sorting. The third method is the adversary arguments. The idea here is to model the computation as a game between two players. The first player is the adversary and the second player is the algorithm. The adversary has the input, it provides the input, and the algorithm asks questions about the input. So you can imagine there's a conversation between the adversary and the algorithm. So the goal of the adversary is to force the algorithm to work harder by trying to adjust the input consistently. So ibig sabihin, consistent yung sagot ni adversary sa mga questions ni algorithms, even though it changes the input with respect to the response of the algorithm. The lower bound for adversary argument is computed by getting the least number of questions the algorithm must ask to the adversary. The concept of problem reduction isn't new. In fact, we encountered this concept when we discussed about transform and conquer as a design strategy. The idea is still the same, and we can use this concept in proving lower bound arguments for a particular problem. So suppose you would like to know the lower bound for problem B and let Q be a problem with known lower bound result. The idea is that we can use Q to get lower bound for P. So that is by getting a problem reduction. So ang sabi is that if problem Q can be reduced to problem P, then Q is at least as easy as P, or equivalently, P is at least as hard as Q. Now, to say that P is at least as hard as Q, we just need to create a reduction from Q to P, and that is by designing an algorithm for Q using an algorithm P as a subroutine. And if there is a reduction from Q to P, then we can say that the lower bound for Q is also a lower bound for P. Hence, we were able to create or identify the lower bound argument for P given a known problem Q.